When we use the internet, we're generally using a host client to access content at a host server over the internet. We are expecting 3 essentials for that session to meet our expectation. First is connectivity. There must be a way for the host client to reach the host server and get the content back to the host client. Secondly, reachability. The address of the host server, the IP address, must be known to the host client, and we described the domain name system earlier, which is the technology used for that, along with protocols like BGP for announcing the routes to reach that host server. Finally, the performance must be acceptable. That is, the defect rate and the delay must be within our tolerance for that content. If it's video, then we don't expect frame freezes and we don't expect pixelation. And if it's a voice over IP, we don't expect the delays to exceed what we can tolerate on a phone call. But to achieve these essentials, we have to go over a network that spans continents and sometimes spans the globe. If we go back to our earlier discussions, we see that the host client is going to be connected by an access network, just as the host server is. And that's going to take us to an IP routing layer, and that routing layer then will go over an optical link via a layer 2 switch in an optical system, typically a wave division multiplex system. So what we have are really connections that are going to go up to intermediate IP routing locations and then onto our host. But I've really simplified the diagram here quite a bit by showing only one IP routing station. This is an IP hop, this is a second IP hop. In a typical host session, we could expect anywhere between 20 and 40 hops to reach our destination, sometimes more, sometimes less. The point is, there are 100 or more network elements that are involved in this one connection. We can run a utility like traceroute and count the number of IP routers in our path, but traceroute will only report the IP routers. It won't report all the layer 2 systems and the DWDM systems. So we should expect on a typical connection about 100 network elements all have to perform for us to be able to have those essentials for that connection and have a successful experience. Moreover, there are other systems which aren't involved in the direct communication path, like the domain name system and like route reflectors, which have to work flawlessly for our session to take place. So now let's take a look at a theoretical model that helps us better understand what kinds of performance and how these networks have to operate for us to meet these essential requirements. Here I've drawn a very simple model of a host client, A, trying to reach a server, B, and pass a request, which I've marked as information I sub 0, through a system S0. So in this theoretical model, S0 passes a copy of the information it receives as I1, and it takes some time t for that transmission to take place. If we have a perfect transmission with high fidelity, I1 will be identical to I0. That is, there will be no errors in the information received by B, and t will be short enough to meet our expectations for the particular service we're using. Now, systems fail. All systems fail at some point, either hardware or software, and links are cut, cable breaks, all kinds of mischief takes place in the real world. We can characterize the performance of this system by looking at 2 variables. The mean time between failure, that is how frequently this theoretical system fails, and the mean time to repair. Given that it's failed, how long does it take us to recognize the failure, to get someone on site that can repair it and get it back up and running again? So I've used 4 hours to repair as an example here, and that's consistent with the industry. There are many types of equipment where that's a reasonable estimate. What does that mean to us? Well, we can compute the availability with the equation I've shown here. If we're failed once a year, then we're out of service for 4 hours in a year. And then I simply divide that by the number of hours in a year and subtract it from 1 to get the availability. So our availability then, that is the probability that that system's going to work when we want it to, is 0.9995, which means we're going to experience 1 failure in 2,000 attempts. That's not a bad number. I'd be willing to live with that as I access the internet. However, recall that we have 100 of these systems in series. Remember, if we use traceroute, we can see that 30 hops is not unusual in an internet connection. And it takes not only the IP router, which is counted in traceroute, but the layer 2 systems, the optical systems. All told, we probably have 100 systems we have to go through. If we do that computation, our failure rate jumps to 1 in 20, which is not acceptable. It means we could not reach sites 1 time in 20 when we try, and that site would be unavailable to us for 2 hours on average. So we have to find a way to overcome system failures in real networks. We do that by using duplex networks. That is, a lot of redundancy is built into the internet. So going back to our simple model, again, I have a host, client A, trying to reach B, but this time there are 2 identical systems in parallel, S0 and S1. Now these are identical systems, and presumably there's some intelligence built into this network so that if S0 is working, then the path will go through S0 to B. But if for some reason S0 has failed, or a link to S0 has failed, then the request will go through S1. So now we have a very different picture of our reliability in our system, and we can find, again, if we assume MTBF of 1 failure per year, in the mean time to repair is 4 hours, our availability now jumps dramatically. Recall before we had 3 9s and an 8, now we have 6 9s and an 8. So it's a much more reliable system because it's the square of the downtime divided by the number of hours in a year rather than just power of 1s. That means we're going to have 1 failure in 5 million attempts with the duplex system. And we have to have 100 duplex systems in series, and I've drawn a diagram here what that might look like. So it's a more complex arrangement for us, but our end-to-end failure rate goes from 1 in 20 to 1 in 50,000, rather than 1 in 20. That is a 2-fold increase in investment. That is, we had to buy twice as many systems, but we got a 2,500-fold increase in availability. So that certainly seems like a bargain. And this is how the internet is designed, with duplex systems. But there's a lot more to it than this, because recall we have to have the 4 hours to repair, which means we have to have systems that are designed, network management systems, element management systems that can detect these failures. We have to have trained operators that can go to the site. We have to have test capability to test and find out which system has actually failed. And then we have to have a whole infrastructure for sparing and repair. But this is the basic notion, that is redundancy, that makes the internet as reliable as it is. Meeting this theoretical model is no simple task. For one thing, the model assumes perfect information at this switch. That is, the switch never makes the wrong choice, switching to a fail system rather than an in-service system. Secondly, it assumes that failures are independent. That is, whatever failure caused system S0 to fail is completely independent and would not repeat itself on a probabilistic basis in system S1. Those are 2 of the practicalities that have to be faced in implementing this system. On the next slide, we'll see how that's actually implemented in practice. I'll begin with the host servers. We've talked about that a bit already. In the website, the host servers achieve reliability through load sharing. That is, there are many hosts typically serving large sites like Google, and the load balancers that serve as the level 2 switches for the host service often have fault recognition and have mechanisms that allow them to send traffic to the working servers rather than those that are offline or failed. In addition, application management is run on many of the host servers that checks the application and restarts it in the event it fails. Finally, for network connectivity, there are redundant sites. So if one data center loses connectivity, a redundant site or other redundant sites can pick up the load. If we moved further into the network and look at critical systems like the domain name system servers and route reflectors, which serve BGP in particular, we see that load sharing again comes into play. Typically these are mated pairs of systems and traffic is shared between the two systems. Caching also helps. If you lose DNS connectivity, if your DNS cache in your host machine has the IP address, then of course it's going to continue to provide connectivity, but you won't be able to access any sites where you don't have the IP address in your cache. So there's some latency between when a DNS server fails and when it might be recognized by the whole served community. Same is true of route reflectors. IP routers maintain forwarding information bases in the routers themselves, and if you lose route reflectors, then you would lose route updates, but you wouldn't necessarily fail routing. The routers would continue to use the information in their bases until the route reflectors come back online. You would lose, of course, any changes in routing that occurred while the route reflectors were out of service. A zone mapping also helps. That is, you don't want to place too large a segment of your network under a single pair of DNS or route reflectors. Your network typically is broken down into zones with redundancy within each of the zones, so you won't lose the entire network if you have a failure. Fault recognition again comes into play with network management systems and made operation, which I've described. Now, as we move into the network, at the routing layer, load sharing again is important. There will be redundant routers for the core, so you'll never rely on a single router within the core for connectivity between any 2 points. Fault recognition comes into play here too, both within the router, which recognizes internal faults and will try to recover on its own, but also via network management systems. We haven't talked about congestion controls, but the level of queue occupancy becomes important in IP routing because congestion can be as deadly as a full failure. Lastly, routing recovery. If we use a routing protocol like OSPF, then we find that the routers keep state tables that disclose the full routing capability and the next hop for any particular IP address. Those route tables are updated whenever connectivity is lost at the IP routing layer. Moving on to switching, and here I'll talk about MPLS in particular, multi-protocol label switching, which is the dominant core switching technology in Tier 1 and Tier 2 networks. There's a technology called fast reroute where label paths are predetermined, and when the MPLS router senses loss of a route, it can switch to the designated backup label switch path or the designated backup route. Performance measurement is also performed typically via independent systems which measure latency across the network and are capable of alerting network management in the event that the performance of the switching layer fails. And then finally move down to the lowest level of network transport, which is optical. A lot of work has been done over the last 3 decades on transport reliability for optical systems, and in metropolitan areas, fault-tolerant rings are dominant. These are SONET and SDH rings, and more recently, wavelength switching is come into play, so the entire wavelengths can be switched on failure. The response of these different techniques is really important. Typically, transport is going to recover within a 1/10 of a second or less. That is, if there's a failure in an optical route and you have a SONET ring or you have a protected DWDM system, they will switch to a good optical path within a 1/10 of a second. At the MPLS layer, we can expect switching within a second. So these are sub 1 second recoveries in both cases. They will be invoked at their particular layers before the IP router has time to recognize that an IP route is lost, and that prevents the router from going into a recovery prematurely. If OSPF has to reconverge, that is, if the routing tables have to be updated across linked state area, it's called, or across a routing area, that can take up to 10 seconds. So we go anywhere from sub 100 milliseconds up to 10 seconds in recovery. There are applications like voice over IP that are very sensitive to outages of 10 seconds or more. Video certainly will take a hit for outages of 1 second or more, so the impact of this redundant switching and recovery is highly application dependent. In the extreme case of voice over IP and some other applications, it may trigger application failures that result in massive re-registration. That is, all the endpoints believe they have lost their registering server may initiate re-registration, called registration storms. So that's beyond the scope of this presentation, but certainly is a topic that's dominant in the industry.